everyone, this is Dr. Compton. He looks like he's out in the field doing some sort of measurement. He lived in the early to mid 1900s and was director of the lab at University of Chicago and won the Nobel Prize. So he was famous for basically what we now call the Compton effect, and that's basically that he found that X-rays scattered had a slightly lower wavelength than the incident rays. This means that they also lost energy. And where did that energy go? Well, this gives rise to this Compton shift. For most practical people, this doesn't have much use. It is kind of an interesting effect, but you're not going to see it in like medicine, at least at this point. So what is Compton scattering? Compton assumed that the photons acted like other particles during collisions, that the energy in must equal the energy out. But what he actually observed was a shift in the wavelength. So the delta of the wavelength was equal to this equation. So the Compton quality is called the Compton wavelength. The Compton wavelength is equal to this value. It's very small compared to visible light. This Compton shift depends on the scattering angle and not the wavelength, and experiments confirm that the results. And this confirmed also that a photon is a particle. So how do we use this math? Here we have the equation. So here we have an X-ray photon, initial frequency of this collides with a free electron at rest. The scattered photon moves off at 90 degrees. What's the frequency of the scattered photon? So what we're trying to find is frequency. So I'm going to change the equation over to frequency base using my wave equation. And then we want to find this new frequency. So I saw that equation for F is equal to C times divided by this fun mess. And then we can put the numbers in and find out that we end up with 2.4 times 10 to the 19th hertz as our new frequency. So we shifted down just a little bit. We started at 3 and we ended up with 2.4.